In this lecture, we'll cover section 1 of chapter 7 on random variables. We'll talk about the definitions and notation used for random variables. We'll look at probability distributions. We'll apply our probability rules to random variables. And we'll talk about how to find the mean and standard deviation of random variables and the rules that govern their use. In the 4 stages of statistics, we're covering probability and random variables. Let's look at some definitions. A random variable is a quantitative variable whose values come about as a result of some random process. We'll see several examples later on in this presentation. When we talk about inference later on, we'll want to be able to draw conclusions about populations based on samples we choose. In order to do that, the thing that we'll consider is how the proportion or the mean in our sample would behave if we were to choose a sample of the same size over and over. This is a random variable. In general, sample proportion and sample mean are complicated. They're hard to work with. So what we're going to do is start by looking at random variables that are easier to get our hands on, and then we will expand the techniques that we learn about to these more complicated situations. There are 2 types of random variables we will consider. The first is a discrete random variable. That's one where the possible values that the random variable can take are finite or countably infinite. That countably infinite is something that you may or may not have seen before, but basically what that means is there is a definite amount of space between each possible value. So the positive whole numbers, 1, 2, 3, etc., those make up a countably infinite set. Something like the real numbers, all the possible numbers you could express using decimals, are not countably infinite. Another way to think of it is a countably infinite set is one that looks like a list. So if you have an infinite set that can be expressed using a list, it's countably infinite. A continuous random variable is one where the possible values can cover everything in the entire range of possibilities over a set interval. So all the numbers between 0 and 10, including all the possible decimals, for example. That would be a continuous random variable. Random variables are typically indicated using capital letters. X, Y, and Z are most common. We'll typically reserve Z for random variables that are distributed normally. We'll talk about how to identify those soon. So, here's our first example of a random variable. Take an ordinary coin and toss it twice. Let the random variable x be the number of tails we see. What are the possible values that x can take? What kind of random variable is this? Well, if we toss a coin twice, the number of tails we could see is 0, 1, and 2. Because there are only a finite list of possible values, that means x is a discrete random variable. The probability distribution of a random variable tells all of its possible values along with the probabilities of each value occurring. We'll often depict probability distributions using a probability histogram, which displays the probability distribution in a way that looks like a bar chart or a histogram, depending on if the variable is discrete or continuous. Back in the last chapter, we looked at the probability values of individual events. When we're looking at random variables and probability distributions, we want to consider all of the possible outcomes that we could get. When we talk about probability distributions, we'll use a few terms that are familiar to us. One is the median. The median, just as before, is the value that's in the middle. Here we're talking about in the middle as the value of the random variable, which represents the cutoff point where half the time the random variable takes a value below it, and half the time the random variable takes a value above it. If we're looking at a probability histogram, that means the value for which half the area is below and half the area is above. The mean of a distribution is the average value. If you were to let the random variable take its value on a long list of times and average up all of the results, the mean is what you would get. We'll talk about how to compute that soon. If the distribution is symmetric, just as we've seen before, the mean and the median will be equal. So let's look at our simple example and compute the probability distribution. Our random variable x is the number of tails we see when we toss a coin twice. What are the probabilities of each of the possible outcomes? What is the distribution? Well, if we toss a coin twice, here are the ways that the coin could fall. Notice that we differentiate between the first toss and the second toss. Each of these is an equally likely outcome, so each of the 4 possibilities we see there have probability 1/4. So, since only one of those tosses, or one of those possible outcomes, represents not seeing any tails at all, they're both heads, x will take the value 0 with probability 1/4. 2 of the possible outcomes result in seeing one tail. So using the OR rule, we get that the probability that x equals 1 is 1/2. That's 1/4 plus 1/4. Finally, only one of the 4 outcomes results in seeing 2 tails. So the probability that x equals 2 is 1/4. So let's take a look at the distribution for this random variable. We've computed the different probabilities for each of the possible values for x. Now, how do we display and summarize our random variable x? Well, the way to display it is with a histogram. On the horizontal axis, we'll list all the possible values for x. And then above each one, we'll make a bar whose height is equal to the probability that x takes that value. So the bar above 0 has height 1/4, the bar above 1 has height 1/2, and the bar above 2 has height 1/4. To summarize this variable, we'll use measures of center and spread, and we'll talk about the shape of the distribution. Looking at the picture, it seems that the mean and the median are both 1, because those fall right in the middle. For the spread, we can say that a typical value falls within probably a little bit less than 1 from the mean, which is 1. We'll talk about how to compute that precisely soon. And the shape of the distribution is unimodal and it's symmetric. We'll use the notation P of big X equals little x to denote the probability that the random variable big X takes the value little x. So in our previous example, the probability that big X equals 1 is 1/2. We might write that this way. The probability that big X equals 1 equals 1/2. Now, if you consider the probability distribution of any discrete random variable, the following things must be true. The probability that big X equals little x must be between 0 and 1 inclusive. That's because this is a probability, so it has to follow the rules of probabilities. Also, if you add up the probability that big X equals each of the possible values for big X, so if you take all of the things that big X could possibly be equal to and add up the associated probabilities, you have to get 1. That's because if you add up all the probabilities of all the possibilities where they don't overlap, the sum must be 1. So if we're looking at a probability histogram and the bars have width 1, then the total area of all of those rectangles must be 1. For complicated processes, it's sometimes easier to break down the process into smaller, simpler bits and list the probabilities of each. We call this process creating an interim table. Let's look at an example of creating an interim table. Let's say that our random variable, x, is the number of tails we toss when the coin is tossed 3 times. What are the possible outcomes? What are the corresponding values of x? And what are the probabilities? So let's create our interim table. If we're tossing a coin 3 times, there are 8 possible outcomes. They're systematically listed out in the left-hand column of this table. Since those are the 8 possible outcomes, and each is equally likely, the probability of each outcome is 1/8. Now, within each outcome, we can count up the number of tails we see, and that would be the associated value for x for that outcome. Using that, we can combine all of the values, outcomes that have the same value for x to find the probability that x equals 1 and that x equals 2. So for x equals 1, we see that there are 3 possible outcomes that result in x equals 1. Those don't overlap, so we can add their probabilities. We can do the same thing for the 2's. So with the same problem, what does the probability distribution and the probability histogram look like? Well, if we look back at the interim table on the last slide, we see that x equals 0 in 1 of the 8 possible outcomes, x equals 1 in 3 of the 8 possible outcomes, x equals 2 in 3 of the 8 possible outcomes, and x equals 3 in 1 of the 8 outcomes. That gives us probabilities of 1/8, 3/8, 3/8, and 1/8, respectively. From here, it's easy to create the histogram. There will be 4 bars, one for each possible value for x, and the height of each bar is the probability of that outcome. So in this situation, where we're tossing the coin 3 times and we're counting the number of tails, what can we learn from the probability histogram? Well, looking at the big picture, the first thing we see is the shape. There's one peak, so it's unimodal, and each side looks the same, so it's symmetric. The center of the diagram looks like, well, halfway between 1 and 2. So we'll say the mean and the median are both 1.5. For the spread, this is a little bit harder to give intuitively, but if we go up and down from the mean, that's 1.5. If we go up and down by 1/2, we get all the possible outcomes where x equals 1 and x equals 2. To get to 0 and 3, we have to go up and down by 1.5. Those values are less common, so the spread is somewhere in between the two. We will talk very soon about computing the standard deviation of this random variable. As a reminder, in the last chapter, we talked about the 3 different ways that we can determine a probability. We can look at equally likely outcomes. We can look at long-run observations, or we can subjectively or intuitively assign probabilities. For the random variables we've been looking at, for the simple ones like flipping coins, we're using equally likely outcomes. For other random variables that we'll be seeing soon, in many cases we'll be looking at long-run observations. For example, in the 2000 US Census, the Census Bureau reported that the distribution of household sizes are given in this table. Reading the table, we see that 34% of all households contain 2 people. What's the difference between how these probabilities are assessed and the way that we found the probabilities for the coin flips? Well, the coin flips were using equally likely outcomes. But the census data, we're looking at a lot of observations. Since each value for X is not equally likely, this is not equally likely outcomes. But the census is derived by surveying many, many households, ideally all the households. So we would say that these probabilities come about from long-run observations. Let's take a moment to remind ourselves of the rules for probabilities. There's the permissible probabilities rule, which says that all probabilities fall between 0 and 1. The sum to 1 rule, which says that if you consider all the possible outcomes and you add up the probabilities, you must always get 1. The not rule says that the probability of an event is equal to 1 minus the probability of that event not occurring. We also have the non-overlapping or rule, which says if events are mutually exclusive, then their probabilities can be added together. We have the independent and rule, which says that if 2 events are independent of one another, the probability of both occurring is the product of the probabilities. We generalize the or rule to take into account events that are not mutually exclusive. And we talked about a general and rule, which is how we compute probabilities for 2 events which might be dependent. Finally, we talked about the rule for conditional probability, which is derived from the general and rule. So looking at our census data, these do satisfy the permissible probabilities rule because each of the probabilities is between 0 and 1. Also, the sum to 1 rule is satisfied because when we add each of these numbers up, we get 1. The not rule is satisfied because, for example, the probability of a household not consisting of just one person is 1 minus the probability that X equals 1, which is 1 minus 0.26, which is 0.74. And you may notice if you add up each of these numbers, take a moment and do that if you want, you see that you do in fact get 0.74. For the non-overlapping or rule, the probability of having fewer than 3 people in your household, which we would denote in this way, P of big X less than 3. Well, we would compute it by taking the probability that X equals 1, the probability that X equals 2, and since those don't overlap, we add them together. The AND rule. Let's suppose we sample 2 households at random. What is the probability that the first has 3 people and the second has 4 people? Well, these 2 events are independent, or at least they are approximately independent because the sample size is 2 and the population size is however many households there are in the United States, which is far more than 10 times 2. So we can multiply these probabilities and we get 0.0224. Now to apply the general OR rule, suppose that we sample 2 households at random. What is the probability that one or the other has 3 people? This is a little bit trickier, but it is true that these events overlap because it could be that the first one has 3 and the second one has 3. So the probability that the first is 3 or the second is 3 is the probability that the first one is 3 plus the probability that the second one is 3 minus the probability that there's overlap, which means that they're both equal to 3. We can compute that overlap by using multiplication, and we get a result of 0.2944. For conditional probabilities, what if we're only interested in sampling households with fewer than 3 people? So we're only looking in these 2 columns. What is the probability that a household with fewer than 3 people is a household with only 1 person? We can compute this using the rule of conditional probability. It's the probability that x is equal to 1 given that x is less than 3. That's the probability that x equals 1 and x is less than 3 divided by the probability that x is less than 3. The probability in the numerator is easier to find than it might look, because if x equals 1, that means automatically that x is less than 3. So if x is less than 1, then x is automatically less than 3. We don't need to consider that at all. So the probability that x equals 1 and x is less than 3 is equal to the probability that x equals 1. The probability that x is less than 3 we computed earlier. We just add the 2 non-overlapping possibilities together. And as a result, we get 0.26 divided by 0.26 plus 0.34, and that's 0.43. Now let's talk about how we actually find the mean and the standard deviation of random variables. The mean, which we denote with a mu, is the sum of each possible value for x times the probability associated with that value. So we take the value, the first value that x could be, that's x1, and multiply by the probability that x is equal to that value. Then we take the second value for big X, x2, multiply that by the probability that x equals x2, and so forth until we've covered them all. We call this a weighted average of the values. So instead of adding them up and dividing by the total number that we have, we take each one and multiply it by the probability of getting each one. The standard deviation of a discrete random variable is the square of the difference of each possible value of x from the mean multiplied by the associated probability for that value. We take all those numbers and add them up, and then take the square root of the result. The standard deviation of a discrete random variable is indicated with a lowercase sigma. The standard deviation we'll interpret as the typical distance of a value from the mean. We'll also talk about the variance of a discrete random variable, which, as before, is just the square of the standard deviation. We're using Greek letters here, just like we used to use for populations, because we are considering all of the possible values for the random variable. That makes this the analog of a population. Let's look at a quick example. Again, looking at our census data for household size. What's the mean? Well, to compute the mean, we take each possible value for x and multiply it by its associated probability. Take the next possible value for x, multiply it by its associated probability, and so forth and so forth, and then add up all those results. That gives us a mean value of 2.5. The median in this case is 2. The way that we compute the median is to look at each value and write down the proportion of all the possible values that are equal to or below it. We go from left to right and add each number to from the previous step to the one that's including in the next one. So 0.26 plus 0.34, that's 0.60. Now the very first number that you get that's bigger than 1/2 indicates the median of the random variable. In this case, the median is 2. Notice that the median is smaller than the mean. And remember when we talked about distributions before, if the mean is bigger than the median, that means the distribution is skewed to the right. And here, sure enough, you do see a lot of values over here to the right side of the mean. It's also worth noting that the median value for x is not the middle value for x. It's not the 4 with 1, 2, 3 on one side, 5, 6, 7 on the other side. We have to take the probabilities into account. Now let's look at the standard deviation. Looking at this list, which one seems like it's most likely to be the standard deviation of the distribution? Here's the histogram to help you. The mean, remember, is 2.5. So to get a typical distance, or a typical value for x, the distance away could be one of these. Which is it? Well, we can rule out a few of them. If we go up and down by 14 from 2.5, we end up way beyond the limits of our possible x values, which go from 1 to 7. Similarly, if we go up and down from 2.5 by either of the two smaller responses, we don't even get the values of x that are near the mean of 2 and 3. The only one that is a reasonable possible value for the standard deviation is 1.4. Again, as we mentioned before, if you look at the distribution, it does seem to be skewed right. Now, we've figured out what a possible value for the standard deviation is. How do we know that it's actually equal to 1.4? Let's look at how to use Excel to compute the mean and the standard deviation of a random variable. Here is the probability distribution for the random variable we've been looking at. Here, big X is the number of people in a random household. The possible values are 1 through 7, and the associated probabilities are given here. How do we compute the mean? Remember, to find the mean, we multiply each value for X times the associated probability, and then add up all those results. In column C, so right next door to the probabilities, I will make a column for the product. And I'll say, this is going to be a formula, so I'm going to start it with equals. It's going to be equal to the X value I'm interested in, right over to the side. I'll push the star key for times. I want to multiply it by the probability. I'll push Enter. Now I've got the product there. I'm going to use my fill down tool to copy that formula and paste it in all the way down. And now to get the mean, I'll add those numbers up. So I'll use the sum formula equals sum of all of those numbers there. And it's 2.52. So that's the mean of our random variable. Now, to get the standard deviation, we need something else. The first thing we need to get is the difference of each individual x value and the mean. So let's compute those here. So this is going to be equal to the actual value minus the mean, and I'm just going to type in the mean, 2.52. And we'll copy that down. Now, if you think back to that formula for the standard deviation, we need to take these differences and square them. So right here next door, we'll do equals that number on the left, and I'll do an exponent of 2. We copy all those down. Now, each of those numbers we have to multiply by the associated probability. So this will be equal to the square of the difference of x and the mean times the probability associated with that value. And we copy that down. Now, when we add all those numbers up, it's the sum of each of these. The result is the variance. From the variance, in order to get the standard deviation, we take the square root, SQRT, of that previous number. Remember on the last slide, we guessed that the standard deviation was about 1.4, and there we see that's right, to 1 decimal place. Now, if you're going to compute these means and standard deviations for discrete random variables using Excel, it's important that you know the formulas, because there is no built-in formula in Excel for finding the mean and the standard deviation of a discrete random variable. Now let's do the same computation, but using our calculators. The first thing to do is take our distribution for the discrete random variable, the different possible values for x and the probabilities, and enter those into L1 and L2 respectively. Make sure the possible values go into L1 and the corresponding probabilities go into L2. Take a second and make sure you've got these entered into your calculator correctly. Now that you have the values entered into your calculator, to compute the mean and the standard deviation, we will quit out of the list, go into the Stat menu. We're going to calculate, and it may seem strange, but we're going to calculate the one variable statistics. So, beside list, we want to choose the list of the values for x, and that was in L1. What's different is we're going to use something here for the frequency list. For the frequency list, we're going to use the probabilities, and the probabilities came from L2. Notice you have an L2 right above your 2 key, so I'll push second, and then L2, and then enter to get to calculate, and then we'll push enter again. Now, if your calculator does not give you this, this set of prompts for the one variable statistics, if you push one variable statistics and it just types in the words one variable stats, the way that you get it to consider both lists is to, after one variable stats, type L1, and then a comma, and then L2. So let's calculate. And what we see here is the mean up in the top row, and you see that matches up with the mean that we got using Excel. The sum of the values, which doesn't seem right. If you add up the numbers from 1 to 7, you don't get 2.52. That's because it's not really adding those numbers up. Because if you look down here, it says n equals 1. That's why also there's no sample standard deviation. Because remember, in the formula for sample standard deviation, you divide by n minus 1, and that results in dividing by 0. But here with sigma x, that's the one we care about anyway, we see the standard deviation of 1.38, which matches what we got with Excel a few minutes ago. Also, if you continue to scroll down, you'll see the computation for the median, which is helpful. You'll also see Q1 and Q3, which we won't be as interested in. So let's look at some computational rules for the mean and for the variance. If you take a random variable and multiply it by a constant, then the mean and the standard deviation are also both multiplied by the same constant. If the constant is negative, we'll need to make sure to take the absolute value before we multiply. If we take two independent random variables and add them together, the result is a new random variable. The mean of the new random variable is the sum of the means of the old random variable. And the variance of the new random variable is the sum of the variances of the old random variable. Now remember, the variance is the square of the standard deviation. So if you want to find the standard deviation of your new random variable, you'll need to take square roots first. You have to square the standard deviations first to get the variances, then do the sum, and then take the square root. We'll use these later on when we're talking about mean and standard deviation of sample proportions and sample means. Here's an example. If you look at the random variable x, where x represents the number that's rolled on a standard 6-sided die, but we get possible values of 1 through 6, and each is equally likely, so the probability of each of those outcomes is 1/6. What are the mean and the variance and the standard deviation of x? Well, we can compute those. The mean and the median are both 3.5. We can get that just by looking because of the symmetry of the probability distribution. Everything is 1/6 on both sides. So the number right in the middle would be 3.5. The variance we can find using our calculator or using Excel is 2.92. Since the variance is 2.92, we can find the standard deviation by taking the square root, and we get something around 1.7. So here is the histogram on the left for our random variable x. Now, what happens if we change our random variable to be twice the number that we rolled? So if we roll a 3, the value of our new random variable is 6. If we roll a 5, the value of our new random variable is 10. What's the mean and the standard deviation now? Well, using the rules we just talked about, the mean will be 2 times the old mean, since the new random variable is 2 times the old one. So we take that 3.5, we multiply by 2, we get a mean of 7. You see that borne out in the probability histogram on the right. Similarly, the standard deviation of 2 times the old random variable will be 2 times the standard deviation of the old random variable. That gives us a standard deviation of 3.4. Now, if we're playing a board game that involves rolling 2 dice, on the left we have the probability histogram for the original. On the right we have the probability histogram for the sum of 2, the number we see as the sum of 2 dice. So what are the mean and the standard deviation of our new random variable? Well, as we saw earlier, the mean of the new random variable, that's the sum of the two old ones, is the sum of the means of the two old ones. 3.5 plus 3.5 is 7, and sure enough, you see 7 is right in the middle of that new distribution. Also, the new variance is equal to the sum of the old variances. Since the variance of our original random variable was 2.92, then our new variance is 2.92 plus 2.92. That's 5.84. So the standard deviation of the sum of the numbers we see on two dice would be the square root of the variance, and that's 2.4. It's important to remember that although means do add together, standard deviations do not. It's the variances that's a measure of spread that adds together. Now, we talked about two ways to get a new random variable out of that old one, the number that we see when we roll a standard six-sided die. And we've seen that the mean of the doubling the roll of the die, that's the histogram on the left, is 7. And the mean of the total that we see on two dice is also 7. But notice that the measure of the spread, the standard deviation, is greater for the one on the left, that's the double the roll, than the one on the right. Why? Well, hopefully you can see it from the histogram. The extreme values here both go from 2 to 12, but notice that getting a double value that's of 2 or of 12 is far more likely than seeing a sum value of 2 or 12. That's because in order to get a 2, that's this bar, when you double the value you see on one die, that's going to happen anytime you see a 1, and that happens with probability 1/6. However, when you're taking the sum of two dice, the only way you're going to see a 2 is if both dice show a 1. The probability of the first one being a 1 and the second one being a 1 is 1/6 times 1/6, that's 1/36. So getting a 2, that's the extreme value on the left, is much more likely when we're doubling. That's why the spread for doubling is bigger, because those extreme values are more likely. For the sum of two dice, more of the area in the histogram is clumped together near the middle than what we see over here with the doubling. That's a really important point. When we're doing inference, we're trying to guess something about a population based on a sample. The bigger the sample is, the more information we get. So if we're looking at adding two random variables together rather than doubling, adding two random variables together comes from finding the value of the random variable twice. That's like a sample size of 2. Whereas doubling involves just rolling once. So taking 2 and finding the average is going to give us a better guess for what's true for the larger group. Put another way, if I handed you a six-sided die and you had no idea what numbers were on each face, and I asked you to guess what the mean value is, would you rather have one roll or two rolls to make that guess? Well, that's easy. The more information you have, the better off you'll be. So you definitely want to average 2 rolls. So in this lecture, we've talked about random variables. We talked about the difference between discrete and continuous random variables. We looked at the notation that we'll use. We looked at how random variables are distributed. We talked about how to display and summarize them using a histogram, the mean, and the standard deviation. We applied the probability rules to random variables. We talked about constructing a table of the distribution, computing that mean and standard deviation, and the rules for working with the mean and the variance of our random variables.